Hi everyone, I'm Yuhsiang Tsai. Today I will present the sparse linear algebra on AMD and NVIDIA GPUs. The rise is on. This work is done by Tsai, Hartwig, and me. So in the past, the NVIDIA GPU is the leading in the GPU market. So we can see the top 500 list. The supercomputer usually use the NVIDIA GPU like V100 and P100. However, we can see the AMD GPUs will appear in the supercomputers in the following years. So for example, like Oak-Ridge, the frontier system will use the AMD GPU. And also AMD use a hip software development ecosystem. So the benefit is the hip programming is similar to the CUDA programming. And their library, the interface is similar to cuSPARSE or cuSPARSE and so on. And we would like to say the rise is on. So by the hip, how can we prepare our Ginkgo library to support different platforms? And also our CUDA kernel also suitable for the AMD GPUs? And what's the different performance across different GPU architecture? So we would like to discuss this one. So we talk a little about the Ginkgo structure. So the previous one, we have a core folder. It includes the library interface and algorithm implementation. And we do not implement the particle implementation here. We use the executor, and the runtime polymorphism will select which kernel we would like to run. So the first one is the reference. So we implement the sequential kernel. It's easy to check whether it's correct or not. And we have also Google test to test some very simple example to verify the correctness. And also for CPU, we have the OpenMP kernel. It's optimized for the CPU, and we also have the CUDA for the NVIDIA GPU. And we also use the Google test to compare the results from device kernel and the reference kernel. So for now, we want to port the CUDA to the heap. So we add a heap kernel. So heap can run on the NVIDIA GPU or the AMD GPU, depends on which GPU card you have. So we also use the Google test to compare the results between the reference and heap. And this is the simple example in CUDA and heap. And we can see the kernel paths, they are identical. So they are not different from CUDA and heap, but the execution syntax is different. So CUDA is use this syntax, but heap give another syntax. So we need to handle this one. So their device kernel can be identical. So we can move the same part into one folder. So we call it common. So common contains the shared kernels. And the benefit is to avoid the code duplication. But we do not put any config in the common folder because we would like to leave flexibility to the CUDA and the heap to optimization. So this one is the flowchart we port from CUDA and to the CUDA heap. So we can see the CUDA, half of the CUDA implementation will go to the common, So the command can be used by CUDA and hip, and CUDA and hip is almost similar. So they just contain some rounding syntax and optimization parameter here. And also hip do not support all of functionality from CUDA, like the warp size cooperative groups. So, but we use it a lot in our original CUDA implementation. So we need to implement the cooperative groups in Ginkgo. So after this, we can output everything into the command. Today we do not introduce how we implement the cooperative group in detail, but I would talk about how we port the SPMV from CUDA to hip, and also how's the performance. The first one is the Loeb Co SPMV. So the detail is in Goran's paper overcoming low imbalance for irregular sparse matrix. So first iteration, each thread will check the next row value. If they are saying they just count the stolen number. And if in the second iteration, it's found the next row index is different from here. So it needs to segment scan to output, because the next iteration will handle the next row. So it outputs the data here. And in the final iteration, because it's finished, so no matter how, it always do a segment scan in the end and output to the output vector. But because there are another segment might have the same row index output, so we need to use the atomic X in the output here. So there are some choices. So if we assign a lot of works, so each works might have a little works, and they can use the context swapping to hide the latency, but the atomic correlation will be much expensive. Or we can assign a lot of work in one warp, so it reduces the atomic X correlation, but it cannot use the benefit from swapping context to hide the latency. So let us introduce a oversubscribing factor to get the balance from the overhead and the latency hiding. So because AMD and NVIDIA GPU properties are not the same, so the parameter should be not the same. So AMD, their GPU class, the warp size always be the 16-fold, and NVIDIA always has the 32 warp size, and the bandwidth and performance is also different. So we need to handle the parameter in different architecture. So we put this parameter before we code the kernel, so we can have the flexibility to optimize the kernel performance. We do not need to use the same parameter in all architecture. So we have more benefit from the parameters. Another improvement is LPAC SPMV. The GPU's thread blocks is here. Each color blocks is continuous thread. So previously we assign each group to each row. It gives, because the result will in the same warp, same group, so we can use the warp reduction to do a very efficient reduction here. But because the LP we store in the color measure, so the memory read is not contiguously. So we just change the how we read the data. So each group we just read one column, and the next group will read the next column. So by doing so, we can read the data very efficiently because the read is contiguously. But because the data on the same row is not in the same warp, so we cannot use the warp reduction here. So we do the atomic add to the shared memory and output to the data in the end. So the previous one we have efficient reduction, but not correlated rate. Current LP we have the correlated rate, but we have the atomic acceleration. So we compare these two performance between in the AMD Radeon 7 and the NVIDIA V100. So Radeon 7 LP, we compare the current one and previous one. So we can see the current one has some very good performance here. And we only have some negative effort here, but in general, we will say the current one is more better here. So in Radeon 7, we choose the current ones. And in V100, they look similar. It's roughly from 0.5 to 2. So we think about it, they are similar. So we also choose the current one here. And also we compare different SPMV on Radeon 7 and the V100 to see Ginkgo vs the compare the Ginkgo and vendor SPARSE. So we take the hipSPARSE of AMD and cuSPARSE from NVIDIA. So we compare the same functionality. So it's a COO vs hipSPARSE COO and the cuSPARSE COO here. So we can see in the COO part, we have better performance in general here. And for the CSR, we reduce the very best performance, but in some cases we also lose. So yeah. And for the LPEC, so it looks in the top of performance, it looks like the similar, but we reduce a lot of very slow performance on vendor's library. And the hybrid is combined by the COO and LPEC. Hybrid will store the regular parts in the LPEC and the irregular parts in the COO format. So it will done by two SPMV from different formats. So it's a comparison here. And we can see we have more usual performance. We do not have very bad performance in the baseline. So also in the CUDA here. And also we use the performance profile to show how the performance looks like. And this one is a simple example of the performance profile. So the left part is the timing results from 3 formats and 4 problems. And the right hand side is the performance profile. So first, we need to take the fastest result to normalize the time to get the ratio. So it will be like this one. And we consider the different slowdown factor and to compute how much percent of the problem. So in the first, we consider the slowdown factor equals 1. So we can choose the yellow part here. And we count it in the S format, we get the 3 of 4, so it's 75%. and 25% and 0% in the first line, we can see here. And we increase the slowdown factor, like 1.1. So it gets a new one in B format. So it will be 75%, 15%, and 0%. And also the 1.2. So for now, you can see A format still be 75%, but B format will contain all problem 100%. So in another sense, so you can see if you slow down, you can along the 1.2 slow down against the fastest one. So you should choose the B format because they contains all problem, but only with the slowdown factor 1.2. So it goes up. So the 1.3 and 1.4, all is the 100%. So this is the performance profile example. So the performance profile can give very many things on the one picture. So in the first figure, in the slowdown factor equals 1, you can see which format has the best performance in all of the problems. So here is the F matrix. It contains the 75% problem, but you can also see which one you should choose if you do not know anything about. You want to choose the better one in general. So like in here, the B format is contain 100% problem. So it means if you can along 1.2 slowdown factor, so you can use B format to handle everything. And this one is the performance profile on Radio 7. So if you can see the Ginkgo CSR is the best performance in all of the problem sets. We choose the 2800 matrix from the cuSPARSE matrix collection. So it's the 2000. So Ginkgo CSR has the best performance in performance in this problem on Radio 7. And we can see if you can along like 1.75 here. So Ginkgo hybrid can handle roughly 90% problems you can along under the 1.75 slowdown. Also in the V100. So we can also see the Ginkgo CSR has the best best performance in here, like 30% here. And if we go up here, so like 1.5 slowdown factor, you can get the Ginkgo hybrid will contain 90% problem here. So after we port the SPMV from CUDA to hip, we also want to know the kernels performance on the different GPU. So we compare the same functionality in Radio 7 and V100. We use same Ginkgo kernels, but maybe with different parameter. So it's the COO here, and the sparse library we compare use the hipSPARSE on AMD Radio 7 and the cuSPARSE on the NVIDIA V100. So we can see the performance here, and it looks like when your matrix contains a lot of non-zeros, the Radio 7 has better performance because Radio 7 has more higher bandwidth and LPAC and CSR. We can also see something like here. So we compare the Ginkgo CSR and the Sparse library CSR and the LPAC. and also the hybrid. But for the Mender library, because we do not know CUDA how CUDA to implement this SPME, so we cannot go to Intel to tell why the performance looks like here. But for the Ginkgo one, we also use different parameters because we need to optimize for different GPU. So there are too many factors to affect on the performance. But in general, it's something like Radio 7 has better performance if you contains a lot of non-zero here, because they have more higher bandwidth. So summary. So AMD and HIP programming language will give another option against the NVIDIA CUDA in the supercomputer. And the HIP and CUDA are very similar and also has a similar interface. So we can use a command to handle this shared kernel, but we can leave the parameter in original folder because we want to optimize for different architecture. So this structure can give to reduce the code duplication and also give easier maintain because we only handle one code base, but we also have the ability to optimize for different GPU architecture. And HIP also allow to compile for NVIDIA GPU. We still have the CUDA and HIP because HIP do not support all of CUDA functionality like dynamic parallel. So we content to CUDA to make sure we can also use the functionality. And we also show the AMD and NVIDIA GPU, the performance comparison in the SPME. So we will say it's comparable. Also, you can consider the price. And for now, the Ginkgo already give the cross-platform SPMV functionality. Also, we already did the iterative solver like CG by CG or GNRES. They also can run on the HIP and CUDA, and also some precondition like ILU or Bragg Jacobi. So they already are in the Ginkgo library. We also store our data and the performance data on the GitHub. So if you are interested in the performance, you can go this webpage, and the plots we generate from this GPE. So you can press on it. And this is the ISC sponsor. And also thanks for your attention. Thanks.